All right, so electrophile versus nucleophile. So electrophiles are electron poor. Nucleophiles are electron rich. Arrows start here. Arrows end here. All right. So we know this, right? So nucleophiles are electron rich, electrophiles are electron deficient. How do I, arrows start here, arrows end here. How do we actually identify these things? Basically two situations that you have seen. I'll do the easiest one first. All right, if I gave you this, and asked for two things. I asked for the products, which we've done before, and then I could ask you, what's the electrophile, what's the nucleophile here? So in theory, this should be rather simple, at least identifying the electrophile and nucleophile, right? The oxygen is the nuke, and then C2 is the electrophile, right? The nucleophile always goes to the electrophile, right? And we could draw the products, hopefully, for this. Balancing our charge, add our lone pairs in. 1 and 2. All right, so that'd be one way. Yeah, I'd want you to be able to identify electrophiles and nucleophiles. So another way I could ask this would be I could ask you for the arrows, right? So in this case, I've given you the starting materials, given you the products, and I said, and I want the arrows. And I could also ask for the nucleophile and electrophile. So hopefully you could see bonds broken, bonds formed here. Let's number our atoms. All right, so in this case, we're breaking a bond between the oxygen and hydrogen, and the pi bond is actually being broken and taking an H. So the bond that we're forming is a sigma bond between C3 and an H, and the bond broken is a sigma bond between H and O4. Now, so hopefully that makes some sense. And then I could ask, which is the nucleophile, what's the electrophile? If I ask that, the pi bond between C2 and C3 is the nucleophile, and the H is the electrophile. All right, we talked about examples of nucleophiles. A lot of it's lone pairs or pi bonds. And then electrophiles are things that are electron deficient, right? Again, this is that classic example. Just because the oxygen has a plus charge doesn't mean it's electron deficient. It's the things one bond away that are actually electron deficient. All right, so nomenclature, naming an amine. So I wrote here NN dimethyl cyclohexylamine. So for all of these, in all these cases, no matter what nomenclature you're doing, you got to identify the parent chain. And it's always the last thing, cyclohexylamine. All right, so cyclohexylamine. All right, so nitrogen's there. All right, so we have cyclohexylamine. This is like the parent chain. Now we got to see what else is off of this nitrogen. So what else is off of this nitrogen? All right, we say NN dimethyl, so it's just 2 methyls. Now, if it had been nothing else as cyclohexylamine, you just put 2 H's there, right? Because nitrogen wants to have 3 bonds. So no matter what, you have to have 3 bonds on there. If there's anything missing that's not a carbon thing, then you just put a hydrogen on there. So RNS, what are we going to do here? So the first thing you need to do is we need to set up the rankings, right? So we started the central atom that's bonded to 4 different things, and we see what it's bonded to. So carbon, 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 carbon. So those are all tied, right? So we need to go one more bond out. So this one, so even maybe it helps to highlight, we're starting at this one right here. All right, so we're gonna look at this one right there for each of those. So let's start here. What is this carbon bonded to? It's bonded to a carbon, a hydrogen, and a hydrogen. So we're gonna write that down. So a carbon, a hydrogen, and a hydrogen.
Maybe it's just me, but I think your screen is frozen.
So like I said, this carbon is bonded to a carbon and a hydrogen and hydrogen. This carbon is bonded to a carbon, a hydrogen, and a hydrogen. This one is bonded to an oxygen, a hydrogen, and a hydrogen. And this one is bonded to a carbon, a hydrogen, and a hydrogen. So unfortunately, I made a really tough one, actually. These are all tied, right? But this one wins, right? So this one will be our highest ranked one. So we call that R1. But these other ones, we got to keep going. So now we got to go out to this carbon, right? So these are gone. This carbon, all right? Out of this carbon. So what is this carbon bonded to? It's bonded to a carbon, and a carbon. What is this carbon bonded to? It's bonded to a bromine, an H, and an H. What is this carbon bonded to? It's bonded to a carbon, an H, and an H. Okay, so let's see. We have high card wins, right? Bromine, carbon, carbon. So this wins. So this would be number 2 then. This would be our red-white, right? Our white one. So W2. Carbon, carbon, tie. Carbon versus hydrogen. This bottom one wins. This would be blue 3 then. And then this would be my lowest rank one, green 4. So that's the rankings. There's the rankings. And then you got to match this to your model kit. All right? And so I can look at this and say, this molecule I drew is S. So let's see if we have something like this acetonitrile that has 1, 2, 3 atoms, 2 carbons and nitrogen. And the question asks, what orbitals make the sigma bond between the carbons? So the first thing you need to be able to do is identify the hybridization states of these atoms. So let's number them. So it's between the carbons. So C1 is sp3 hybridized, meaning it has 4 hybrid orbitals. And they're all sp3 hybrid orbitals. How did I know C1 was sp3 hybridized? It has no pi bonds and it can't do resonance. C2 is sp hybridized. So that means it has 2 pi bonds. It means it has 2 p orbitals. And the other 2 hybrid orbitals are sp hybrid orbitals. So C2 is using the p orbitals for pi bonds. And the other ones it's using for sigmas. And C1, right, is also bound. They're not in there, not drawn in, but it's bonded to 3 hydrogens. And so it's using those sp3 orbitals to make 4 sigma bonds. So if you're looking for the sigma bond between carbon 1 and carbon 2, it's between an sp, all right, so C1 to C2, it's an sp hybrid orbital from 2, and an sp3 hybrid orbital from C1, making that sigma bond. Okay, so let's say you're given this molecule, and I ask you to draw the most stable chair conformation. So what you're going to need to do is take this and draw it on 2 chair structures, one leaning to the right, one leaning to the left. Doesn't matter which one you do first. I number these carbons. Doesn't matter how you number it as long as you're consistent. This is technically the right way if you're numbered for nomenclature, but I'm not asking a nomenclature question here. I like to think of the wedges as up, the dashes as down. I like to label, just for me, for ease of things, put the top one as 1, 3, 4, 5, 6. So before I'm putting anything on there, I'm just doing this chair flip in my head. What happens in the chair flip? 1 comes down, 4 goes up, right? The head gets pulled to the feet. So this is now 1, 2, 3, 4, 5, 6. So if carbon 1 has an OH right here, and it's down at this carbon 1, the position that's down is equatorial. Carbon 2 has the methyl and is pointed up. At carbon 2, the position that's up is also equatorial. At carbon 4, the position that's up is also equatorial. Okay? Now we're going to do the flip. So whatever is up stays up, whatever's down stays down. But what changes is axial and equatorial. So carbon 1 had an OH that's equatorial and down. After the ring flip, the OH is still going to be down, but instead of being equatorial, it's going to be axial. Carbon 2 is going to be axial and up, or the methyl. And then at carbon 4, this tert-butyl, this big group, was equatorial and up, so now it's going to be axial and up. So there's the ring flip. Hopefully you can see that. So you got to know the positions at each one of the carbons, right? The axial and equatorial, how to draw those. Be able to see if they're up or down. The most stable one is going to be this one, because everything is equatorial. You want the biggest groups equatorial, and if they're all equatorial, that's the best thing you can hope for. So that's the most stable one is that, right? Yep, so just, to answer that, that's a good question, right? It doesn't matter if you drew this one first and then drew this one, it doesn't matter. That's fine. It doesn't matter. And then you got to circle so whatever one you want to start with, or however you want to do it, that's fine. Yep. So let's think about electronegativity and acidity. So electronegativity is the main periodic trend as you go across the periodic table, not down. So if I'm asking a question about electronegativity, it necessarily means I'm asking about comparing things across the periodic table. So, right, carbon, nitrogen, oxygen, fluorine, silicon, phosphorus, sulfur, chlorine. Yeah. All right, I could put HCl in here too, right? Versus that one. So all I'm asking here is, right, like there's a couple ways to think about this, right? Remember I always said there's two things that make a reaction happen. One of two things or both. Reactive bonds, reactive starting materials, and or stable products. So you could look at this a couple ways. You could look at it in terms of how reactive these hydrogen bonds are. Probably need to have another one there. Right, these bonds in here too. Right, these bonds, how reactive these bonds of hydrogen are. That's by looking at how polar they are, like the difference in electronegativity. So hydrogen stays the same in all of them. So the only thing that's changing is this silicon, sulfur, phosphorus, and chlorine. So you'd want to see where those at in relation to each other on the periodic table. So there they are. So chlorine is the most electronegative. Silicon is the least electronegative. That means it'd have the least polar bond. So this would be the least acidic. This would have the highest pKa. This would have the lowest pKa. And then it would go, let's see. So it would go by rankings. So this would be the most acidic. All right, so if I said most is 1, least is 4, this is 4, this is 1, this would be 2, and then this would be 3. So that's looking at the starting materials. You could also look at the conjugate bases, and let's do this quick. Right? What's the conjugate base for all of these? All the conjugate base is if it lost that hydrogen got taken off. And then you're just looking at like negative charges. Who's happier with a negative charge or more stable, less reactive with a negative charge? All right, so you can look at these things in terms of how reactive the star materials are or how stable the products are. And then the opposite is true here, right? Chlorine is the most stable, right? Because it's happiest with a full octet, right? Most electronegative. And this would be the most reactive, right? Conjugate base. So that's another reason why I say that this isn't that acidic, because it doesn't have a very reactive bond and it doesn't have a very stable product. So you can look at the products or the starting materials to answer those kind of questions. So for Newman projections, I just want to make sure when people are drawing an eclipsed one, so this has come up quite a bit. So this front carbon, 1 and then 2's in the back. If things are eclipsed, it doesn't matter if they're like both if this thing's on the right hand side or if it's on the left hand side. As long as it looks like eclipse, that's what matters. So there's no right or wrong way to make sure those things look that way. Otherwise, let's see. Let's try to draw. Let's take a Newman. Let's take this one and see if we can draw it as a wedge and dash. All right. So, taking Newman projection, drawing as wedge and dash. So first we got to recognize this is eclipsed, and they're both kind of pointed up. I always think of it as a head. So before I even draw anything in, I can draw this. Right, match it there. Number my carbons, so 1 and 2. So I'm pretending I'm looking at it right here. I could draw my little person, the eyeball, that I'm looking this way. So at my head, I'm carbon 1. Hopefully you can see that there's an H. On my right-hand side is this kind of longer carbon piece. It has 1, 2, 3, 4 carbons. So make sure I don't lose any carbons along the way here. And then there's a bromine on my left. Right, that's on carbon 1. There's an H on the same side as bromine. So that's going to be hatched back here. There's a chlorine pointed up, and then a 2-piece ethyl right there. All right, so be able to interconvert between, right, recognize this as eclipsed, be able to draw this is important, and then vice versa, be able to do that too. So then again, stability, right, wise, eclipse is always higher in energy than staggered, right? So if something's eclipsed, it's always going to be higher in energy than staggered. So just know that, and then what you want to do is get the larger atoms away from each other, right? Longer change, bigger atoms like bromine and chlorine. You don't want those things on top of each other. So when you're looking at eclipse structures, you want the bigger things farther apart if possible. Same with staggered. You want the bigger atoms farther apart. Okay, so a couple resonance examples. The two different ways you'll see both reactions and resonance is either I'll give you the star material and the product and ask for arrows, or I'll give you the star material and arrows and ask for the resulting resonance form. Notice the resonance arrows. So for these ones, I always think it's really important to number your atoms that are part of the p orbital system. Make sure you got to recognize, in this case, right, 1, 2, 3, 4, 6, 7. These are all lined up. For carbons sp2 hybridized, if it's a carbocation, carbocations are always sp2 hybridized, meaning they have an empty p orbital. They have that empty p orbital. Now some might ask, right, okay, let's draw the arrows. This is easy, hopefully. The pi bond breaks. These electrons go there because we're making a new bond between the atoms. So 3 has a plus charge. You can keep going around the ring, moving this. I would caution moving this bond. Now, why is that? Because you'd end up with a plus charge in the oxygen, and the oxygen wouldn't have a full octet, so that would be really less likely to happen. So you move the electrons around that way. For this one, right, again, you can see this oxygen's next to a pi bond. The oxygen itself doesn't have any pi bonds, but an atom with lone pairs next to a pi bond means it can do resonance. So this is going to be sp2 hybridized, and this lone pair is going to be in a p orbital. Right? Number these atoms. 1, 2, 3. Nothing changes over here. We made a new pi bond there. then hopefully you notice there should be electrons there. We got to balance our charge, right? Balance charge up there. We made a pi bond, and we moved electrons to an atom. So 1, 2, 3. So this is showing a resonance form, but we moved them to the atom. So we're going to look at a starting material with arrows and drawing the product, or given the starting material, or giving them one resonance form to another, and then be able to draw arrows to form that. It's something you should be able to do. So I can keep going around for this one. All right.
No, this one.
All right, going around for that one. Plus charge there, and you could move this pi bond, but then that'd be a non-full octet on that oxygen. Be careful, right? Again, so if you're asking down here though, right? This starts out with an overall negative charge. You have to have an overall negative charge. Balance your charges. You got to balance the charges. No matter what you do, you got to balance the charges. So ranking Newman projections. So again, recognizing staggered versus eclipse, and realizing eclipse is always higher in energy. So for these, I had to have 3 examples. So hopefully you recognize the middle one is eclipse, so that's going to be the highest in energy. Right, that'll be the highest in energy, potential energy. And then between these two, if we want to look at it, between like, if we go A, B, C, between A and B, I would get, or A and C, excuse me, so B's highest. Between A and C, though, I would guess A was a little higher, and here's why. Is because 60, this bromine's sitting between these two CH3s, whereas here the bromine's sitting between a CH3 and an H, right? So this is a little more crowded, right? Atoms a little more closer together here, and then this bromine's also right there, 60 degrees from that one, whereas there's a little more space in C. So I would rank these potential energies as B is by far the highest, then A, and then C as the lowest energy, right? Just looking at where the atoms are at in these Newman projections.